So for today, we get to review a little bit about cosecant and secant, because that's what I taught you yesterday. We're going to start with that, and then we'll go into pretty quickly practicing tangent and clarifying how it's different. All right, so cosecant, right now there's kids graphing sine because they know that it rides on the back of sine. How high you go up, it's kind of a personal artistic decision. I'm going to say that's 1, I'm going to say that's -1, and this is 2 pi over 2, and then I think it's smart to go 1 pi over 2, 2 pi over 2, 3 pi over 2, and 4 pi over 2. Cool. There's sine. Then cosecant is 1 over that. So wherever this one was 0, 1 over 0 wouldn't exist. That's why the asymptotes are there, there, and there. You on your phone? Are you on your phone? Okay, can you put your phone up in the phone jail, please? All right, so the loops go like this. And how many of you had that right? Raise your hand if you did. Cool. Okay, so then let's not even redraw it. I mean, that's dumb to have to do all that effort to redraw it. But let's do this little tweak, which is push it which way? That's called a phase shift. Left or right? Left. That's left pi over 2. So the first thing I would do is try to figure out how far is pi over 2. And then I would draw arrows to the left for all the key stuff. Now, do I really need to transfer sine over there? No, I don't. Sine isn't even really in my graph. I told you I'd probably be pretty nice about kids who forget to erase it out, because it's kind of like showing your work. But at this point, I don't want to have to move that. So I'm going to move everything to the left, pi over 2. And I hope you saw that there's a pi over 2 right here, which tells you that one mark, like from here to here, that is how far we're going to move everything, including the asymptotes. So I'm going to make a line for those too. 1 mark over. This dot here, 1 mark over. This asymptote, 1 mark over. This dot here, 1 mark to the left. This asymptote, 1 mark to the left. Then on a real test, I would erase them as I went, because it gets really messy. I don't want to erase them all, or you won't see where they came from. I'm going to change colors. I'm going to make my asymptotes green now, and they're all going to go 1 mark to the left. And then my loops, 1 mark to the left. Now I know there's way too much info on that screen, but I think if you concentrate, you can see that the green one is your answer, and it just got moved. Pi over 2 to the left. That's 1 mark to the left. All right, things I'm worried about for the test. Yes, question first.
On the last one, can you not just like start by drawing out or writing out the x-axis, but just change, like you can't change just the axis numbers?
No, you can't just change the x-axis numbers. Yep, that would be wrong. Don't ever change the x or the y-axis to be shifting. You can change them if you want to multiply everything by something.
Yeah.
But the problem with that is if you shift them, then all of a sudden 0, 0 isn't 0, 0 anymore, and it's just too far off of reality. So if you ever want to multiply across the bottom, totally cool to do that. Or change this to a 7 and a -7. Those are fine, because those are multiply bys. But if it's ever a shift, don't change your x and y numbers. Just actually shift the whole graph. Okay, and if you're ever on a test and you're like, can I do this? You could ask me that. All right, I think that's enough for cosecant. Just a thought, if you were asked to graph secant, you wouldn't graph secant first. You would graph what? Cosine. And then you would do the asymptote thing. All right, now go to this page. This is tangent. So I want to tell you, I think a good teacher tells you why something happens instead of just memorize this. All right? I see a couple cell phones out. They need to go away. I know you're not using it right now or going phone jail, but can't be on the desk. All right. So tangent is sine over cosine. True or false? True. The top can never be 0. True or false?
False.
False. The top can be 0. The bottom can never be 0. True or false? True. Do you get then that cosine being 0 sometimes, which it is, means that creates the asymptotes for tangent. The hardest thing to remember about tangent is where is the asymptote. So I'm trying to give you a way, if you forget on the test, and if you go, okay, what is tangent again? Oh, it's sine over cosine. So wherever cosine would have its asymptotes, would you please write on the graph sketch cosine, which goes like that, right? Do you get now why tangent has an asymptote there and there? It's because cosine goes right like that, and wherever cosine is 0, you'd have the asymptote. Okay, so then this, well, you have to tell me. Don't say it out loud, but would you please label this and this? Well, you know it ends at 2 pi, right? So clearly it's not at 2 pi. And clearly it's not right in the middle. Pi over 2. And if I wanted to count it, it'd be 1 pi over 2, 2 pi over 2, 3 pi over 2, and 4 pi over 2. And which ones have asymptotes? Pi over 2 and 3 pi over 2. Does that make sense to you? All right. Now we could graph our tangent in here. And it would look like that. And that's not wrong. You can go ahead and draw that in. But that's not where they usually draw it. Why? Because if I continue my cosine, I hope you get that it would go like that. And so there'd be another place to draw it, and it would be here. Do you get the fact that it's right by the origin makes that kind of a desirable place to graph your tangent? And they're identical to each other. So most of the time, I see people graphing this one. But if I was asked to graph tangent, one period of tangent, I'd be fine with this one that goes between pi over 2 and 3 pi over 2. That'd be okay. I'd take either one. But I will tell you this one has got a lot of like logic to it. Later on, we'll be referring back to this one a lot as, you know, like, why is this happening? This is positive pi over 2, this is negative pi over 2, and that makes a total of 1 pi is its period. Let's talk about that. That's different, and it's really important. Okay, so the top number one thing that kids get wrong on about tangent is that when you go do its period stuff, people are like, well, tangent? Oh, the period's always 2 pi, right? No, not on tangent. Tangent's period is pi. So in that big famous equation that I said would come up by the end, by the test, period is 2 pi over b. No, it's not. What is it for tangent? Pi over b. Because tangent has a period of pi normally. Okay, so that's a really easy mistake to make because 4 of the 6 functions have a period of 2 pi. It's just tangent and cotangent that have a period of pi, yes?
Is there a reason that the tangent, the graph for tangent looks a lot like the x cubed graph?
It does look a lot like the x cubed graph, but it isn't exactly the same curvature. But as far as a reason, I don't have a good reason why it looks like that. I would often tell kids it kind of looks like that, but I don't have a good, like, there is no mathematical tangent is like x to the third. It's not quite that simple, but they do kind of, they look very similar. Yes?
So I'm a little bit confused what it looks like that, because like for cosecant and secant,
Yep.
it's like the 1 over the cosine and sine. That's kind of easy to tell. Why is tangent look like this?
Why does it look like this? Okay, fair question. Let's go back to what tangent really means. Would you agree that it's sine over cosine? So if I were to graph sine on the same graph with cosine, okay, I'm going to do that. You don't have to because I think it's going to get really complicated looking, but if I graphed sine on the same graph as this, and one more thing, this must have been where 1 was. And down here at the bottom of the, like the bottom of the valleys, that's where -1 is, right? Remember how it's sine divided by cosine. So sine divided by cosine at each spot. I can't give you, other than if you take these two numbers and divide them, this, no, that's tangent, sorry. This number divided by this number, you will get this number. All right. Okay, so, and generally it looks like an x to the third graph. Okay, one more thing, and this is really important because I left it out, and kids always leave this out on the test, and then it ends up biting you when you have to shift it. You need to know what's in between. So far you've only had to know 2 marks, pi over 2 and negative pi over 2. And for extra bonus, you might want to know that this is 3 pi over 2. But back to this, you only had to know 2 things. That was a little too easy. Do you remember all the other functions? You had to remember 5 spots. 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, and then also 0, 0. All of those, that was the 5 spots you had to graph every time. Well, this needs you to remember at least 2 more. What's exactly between this, which is 0, 0, and this, which is pi over 2? What's exactly between those two? Pi over 4. And then, logically, negative pi over 4. And why do those spots matter at all? Isn't it just some random place? No. It's exactly where the graph will equal 1. Now, if I had drawn this perfectly, sine and cosine, let me clean this up a little bit and make it better. At that spot, you were asking why is tangent drawn the way it is. At that spot, do you see how the green line and the red line go through the exact same spot right there? So it makes sense that it would equal 1 right there. Okay? So this graph is not it is not perfect. That red line, I really probably could have graphed these perfectly, but I was just trying to give you an idea. At that moment, they would equal 1. So this bright green blotch actually is right exactly where those guys are, is 1. Same thing down here, where this touches, that's at -1. So these middle spots, there's so much like symmetry going on. Those middle spots happen to line up exactly where you have 1 and -1 on your graph. And why is those spots so important? Because if I go throw in a 7 right here, you all know, oh, I'm just going to go change my y labels to a 7. But if you didn't have any 1 and -1 on here, you wouldn't know where to change it. But if I have a 1 right there and I can say, oh, now it's a 7, and now it's a -7, then it makes more sense. All right. Glad you're here. Okay. All right. That'll work. Okay. So, just taught you what tangent was. Let's see if it actually stuck. All you're going to have to do is change this to have an 8 on the y-axis where it was going to have a 1. And don't do multiply by 2 at the end. Just wait to graph regular tangent first. And some people are going to do different spots, but I would recommend you get used to this one right around the origin, because that's where we usually graph tangent. It does repeat in other spots, but... And most kids are not awesome at drawing that, and I'm not going to mark you down for not having the perfect curve. Don't expect that to be perfect. Mine's terrible. How many of you knew it was pi over 2 and negative pi over 2? Okay, that's hardest thing to remember about this is where are the asymptotes. Do you get, we could have graphed sine over cosine and then pieced together that, oh yeah, it's where cosine hits 0. If I was doing cosine, it would have been like that. And that's where cosine hits 0. All right, did you remember to mark the middle spot? If you didn't, you should do that now. Because on the test, if you don't have that spot, you won't be able to do the vertical stretch. Shoba, where is that spot right here? What do I label this? Correct. And the other one? Correct. Okay, cool. Then there's a dot here, and there's a dot here. And they are at 1 and negative 1. And we're going to go change that to an 8 and a negative 8 because of this. And all my x values? John Rafferty, what do I do to all my x values?
Multiply by 2.
Close.
1 over 2.
Yes, multiply by 1 over 2 on all of these. So you'll start getting the hang of it that, oh, be careful. If I actually multiply them each by 1 over 2, this would be 1 pi over 8, and this would be pi over 4. I thought you could always count up. You can. 1 pi over 8 could become 2 pi over 8, which would be the same as pi over 4. Pi over 4 and 2 pi over 8 are the same exact thing. But if I'm counting, I'd rather count by something like consistent, like 1 pi over 8, 2 pi over 8. So that's what I would do. I would make this 2 pi over 8. And then at the end of the test, I'd go back and try to reduce things. And this is negative 1 pi over 8, and this is negative 2 pi over 8. And that's because of this 2 here. All right, so if I asked you what's the period of this thing, I hope you'd be like thinking, okay, he said period of tangent is pi. But this one's been changed. This does not have a period of pi anymore because of this. Write down the little formula I just told you 3, 5, 10 minutes ago. Period is what again? Pi over b. And what's b?
2.
So the period is pi over 2. Done. Now if you wanted to figure it out from this graph, you'd go, well, how far is it to here? 2 pi over 8. How far is it to here? In a distance, it's 2 pi over 8. So total, 4 pi over 8. What's 4 pi over 8? It's pi over 2. So memorizing this formula is powerful. We're going to need it again tomorrow. Yes? What is the amplitude? It's 8. Okay. This one, cotangent. Okay. So here's what most kids think on cotangent. Well, I'm just going to put the asymptotes right back where they were, and I'm going to flip this thing over because I know it's 1 over the other function, right? So then it must look like that. You're close, but you're not right. The asymptotes aren't there. You'd think they would be, but they're not. So let's go back to what cotangent means. Is it sine over cosine? It's cosine over sine. So it's where sine is 0. So there's where sine is 0. So those are the spots where you'd have asymptotes. Once again, we usually do the one closest to 0, 0. So you may want to have one good graph of cotangent. And it does get flipped because it is 1 over tangent, but it's flipped and moved. So the asymptotes are not where the other ones were. This one's at pi, and you never have to label 0, 0. I'm putting a 0 there just to make it really clear that the period is pi. Get it? It completes between those two asymptotes. It gets a complete cycle done. So 0 to pi, so the period's pi. Just like on tangent. So it's that green line with the blue asymptotes. Does it replete? Sure, but don't just like, I'll just do 2 of them for good measure, because now you just did 2 periods of cotangent. And unless they asked you for that, you'd be implying that you think that it takes 2 of them to make 1 whole. It doesn't. So don't graph more than you have to. That would be true if they asked for 2 periods of it. Okay, and then what else could we do? Well, of course we could do this, and that's super easy actually. Oh, wait a minute. I don't have my y values. So everybody put in the y values of 1 and -1 first, and then we'll stretch it in a second. But just like before, this isn't going to be just some random spot. It's exactly halfway between the middle and the asymptote. And so if this spot here is pi over 2, then where do you think it is? Pi over 4. And then if you can count, 1 pi over 4 reminds me of the count on Sesame Street. 1 pi over 4, 2 pi over 4, 3 pi over 4, and 4 pi over 4. Cool. Now I've got enough accuracy to be okay for regular cotangent. But what if I wanted to do 40 cotangent? Well, I need to just change this to a 40 and this to a -40. What about this pi over 2 right there? Do you get, I'm not going to just multiply by pi over 2. I'm going to multiply by the flip of that, which would be 2 over pi. Question?
Would be wrong if you had those simplified, like.
I'm okay with you simplifying. But I do recommend this because when we ask you, like, what's this spot, which we do, I'm not telling you exactly how we ask you that, but you got to be able to say, oh yeah, that's 5 pi over 4. There's no problem. Whereas if this was just pi, you'd be like, I don't know. So counting this way really does help find the next spot. Okay, but I'm always, what am I going to do? Mark it wrong because you reduced? Pretty weak ground to stand on as a teacher. You reduced it, so I'm going to mark it wrong. All right, so pi over 2. Do you get how I just multiplied by 2 over pi? Because it's always the opposite of what you would think. So I don't multiply by pi over 2 that I saw here. I multiply it by 2 over pi. And that makes the pi's cancel. So then all of a sudden this pi's gone, and I have 2 pi over 4, which is 1/2. Or 1 over 2. So this must be 2 over 2, and this must be 3 over 2, and this must be 4 over 2. And the pi's are gone because they put in a pi that would cancel it. One over 2, 2 over 2, 3 over 2, 4 over 2. All right, and this was a ludicrously easy lesson, and I am tempted to just say, so here's some work time to work on 3 hard problems. But you'd finish these and still have time left over, but I know you think that sounds great, but let me just give you a minute of tomorrow, because tomorrow's really hard. And I believe the more I learn about the human brain, that you can work on things in your subconscious. And so if I give you a problem today and help you understand it today a little bit, then overnight, in the back of your mind, you'll be thinking about this. And that means by the time you hit tomorrow, you'll be able to understand the lesson way better tomorrow. So imagine there's a post for a dock. Here's your dock. Nope, the dock wouldn't be there. The dock would be up above this post. So I'm going to make this post like really tall and say, here's the dock whether you go stand on it. This is called a pier. And we don't have these in Minnesota. We have docks, but we don't have piers because that's what you have out over an ocean. All right? So now here you are standing up on the dock, and you're down in Florida on spring break or something, and the water level is here. Well, if you look on your iPhone, you could even just ask it, when is high tide? And Siri's smart enough to go, where is he? And what is the tide table? And they'd be able to say, high tide will be at 8:02 p.m. or whatever. All right, so you figure out, and a lot of docks will be labeled at the water level. Okay, so let's say that this is 10-foot deep water. Let's say that at high tide, the water's up here at 14-foot deep. The most crazy tides I ever saw in real life was in Alaska. I don't know if you know this, but at the equator, there's not much for tides. It doesn't really change much. But up in Alaska, the tides are massive. It can be like 15 feet different at high tide and low tide. And so you'll actually have places where at low tide, the boats will just be sitting there on their side, waiting for the water to come back. And then at high tide, the water will flood in, and then the boats just lift up and they can, sail away. So they're massive tides at northern, higher latitudes, and not much at the equator. So imagine this is your scenario, and the low tide's at 10 and the high tide's at 14. Would you agree that the water level, of course, goes between them, and it does it over time, and it almost might look like that if you graphed it, which doesn't that kind of look like a sine wave or a cosine wave? See what I mean? So would you agree that down the middle of a sine and a cosine wave is where zero normally is? That's where the zero line, it's called the baseline, or I like to call it the center line. It runs right down the middle. That's normally at 0. But in this case, where's the center line in this one? No, it's not at 10. It's between 10 and 14, so it's 12. So, if I wanted to write the equation for this, we always use cosine because of a little trick. But I like everybody to write A, cosine, B, theta, minus C plus D. And I could put this as a plus. I guess I don't have any good reason to call it minus. Although, okay, I'm going to make it minus because we usually do make it a shift to the right. So there's A, B, and C, and D. Do you remember anything about them? What's A again? It's amplitude. I can look at this chart and I could tell you the amplitude. Could you? What's the amplitude of this thing? Some kids are going to say 4, other kids are going to say 2. What do you think it is? The amplitude's 2 because it's from the middle line up, from 12 to the 14. So above your amplitude, you can put a 2 in this case, or below it. Y equals 2. Always use cosine because of, where the peak of cosine usually is? Where it starts, right? So the XY axis could be like this. And do you agree that unless you get lucky, your highest tide isn't going to be exactly at time 0? Okay? So that distance right there, that is the X value, which is always time when you're talking about tides, of the peak. So that, again, Google can tell you that happened at, let's say, 8 p.m. That's when high tide was. Let's say at 12 a.m., which is how many hours later? Let's say 4 hours later is when low tide was. Do you get that means 4 hours is not the period, but it's kind of like how you're going to figure out the period? A lot of people go highest to lowest. That's the period. No, it's not. You got to complete a whole cycle. So you go all the way down and then you got to come all the way back up. That is a full period. So if I tell you it's 4 hours between the high and the low tide, do you get the period is actually 8 hours then? Ah, if I know the period, can't I figure out this number? Because there's a little equation for that. Period is this the one where it's 2 pi over b? Or is this the one where it's pi over b? Think. One of you said pi over b, one of you said 2 over. Oh, now they agree, it's 2 pi over b. Because this is not tangent. Okay, so period is 2 pi over b. So if I told you the period, which is, in this case, well, it was 4 hours, and some kids are going to write 4 hours, and they'll get it wrong, because that's half of the period. So it's 8 hours. If the period's 8 hours, I can then figure out what b has to be? It ends up being 2 pi over 8. Because I can just solve that for b. This c is the x value of the first peak. That's this spot right here. And that happened at 8 p.m. So minus 8. These are weirdly in time. But that's when the real world, you don't measure what was the angle when I hit the high tide. You're measuring what was the time when you got the high tide. So these are times. And last but not least is d. Come on, think about it. It's been shifted. The whole thing got shifted from 0, 0 the center line used to be at 0, but it's been shifted up to 12. There it is. Now I've pre-taught you tomorrow's lesson, and some of you already have it. I'll go over that again, but that's the hard part for tomorrow. So they're going to give you a chart, like high tide, low tide, and you're going to go, okay, what time was the high tide? What time was the low tide? And then you just got to remember that that's not the full period. That's the most common mistake. High tide to low tide is half of a period, because it has to get back to high tide again to have completed the complete cycle. All right, now I've pre-taught you tomorrow's. But you need a little bit of time to work, so those 3 homework problems are what you should focus on for tonight. Please save questions on this for tomorrow, because this is what I'm teaching you tomorrow, so I don't want to work on that right now. I really haven't explained it well enough, but I gave you a start, so that it should make it easier tomorrow. 3 questions for tonight, yes?
Is tomorrow going to be the final lesson of this
No, tomorrow is almost the final lesson of this unit. And we do have a lab thrown in on this unit, which is about real world tides. And you're going to like pick a city and you're going to look up what is high tide and low tide in that city. Because some of you guys vacation in Florida and maybe you want to do that. Maybe you dream of living in Hawaii someday. We can see how big the tides are there. Maybe you want to be in Alaska someday. My daughter, his dream was to live in Alaska. So maybe you want to do Alaska. So you get to look up the city, look up the tides, and then you get to write an equation like this from the real world. It'll be kind of cool. All right, and that's all I have for you for the video for today.